So firstly, like I said, we're just going to have one more test. It'll be take home, okay? I will probably distribute that in the middle of next week, like on Wednesday or something. Okay, so that'll be the last thing you work on. I wanted to spend a little bit of time talking about the Zoom sessions for the capstone presentations. So those apparently will happen on the 20th, like all three of them, just boom, 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 yeah? And they tend to be relatively short. It just sort of depends on who's running the capstones, but they tend to be relatively short, usually 20 to 30 minutes or something like that. So if you can, I would really encourage you to attend those and you know, and get that piece off your plate. I think that they will be recorded, so you'd be able to kind of watch them later if you're not able to attend during that exact time. Okay, I'll sort of make sure that Dr. Wright records those things. We've done that sort of thing in the past just to accommodate people. Okay, so remember, I wanted you to attend 3 talks, and it turns out there's exactly 3 this semester. And they're all just right there on that day, right? But you guys have been giving talks. We've kind of been doing the history talks in here, which has been good to just kind of expose you to some of that for sure. The last thing I want to do is talk about a couple of things. One is the movie that we watched last time, okay? So I'm just curious. Well, first of all, let me pose a question, and then I just want to get some insight and input from you. You know, I think they did a great job putting it together, especially for sort of a general audience like that the BBC would have had. There was some stuff that clearly most people wouldn't understand, and in fact, a lot of mathematicians don't necessarily understand, but they kind of gave you enough of the basics that you could kind of see the struggle that Wiles went through, sort of personally, and also even how the argument worked, which is remarkable because I don't know if you noticed, but the proof is like massive. I mean, it's like hundreds of pages long, okay? But they were able to kind of pinpoint the key elements of the argument, kind of the foundational principles of the argument. And I thought that was really good. There's actually a book written by Simon Singh, who was actually the director of that film. And it's supposed to be kind of for the lay mathematician, basically. It reminds me of Journey Through Genius, actually. He actually wrote 2. One is called Fermat's Last Theorem, and the other one is called, oh man, I can't remember the title right now, but they're both like fantastic books. Both of them by Simon Singh, both having to do with Fermat's Last Theorem. And what he does is he kind of tries to walk you through, which is amazing, sort of the basics of the argument. That was the goal with the book. There was actually 2 mathematicians that were simultaneously competing to write a book like that. One by the name of David Brassoud and Simon Singh. And Simon Singh kind of beat him to the punch, okay? There are other like major hallmark results and proofs in mathematics that were really hard for the non-specialists to understand, that people have tried to like synthesize for the common mathematician. And Simon Singh did that in the case of Fermat's Last Theorem. So there are 2 books that I would highly recommend to you. Man, what was the name of the other one? I can't remember. It's sort of escaping my mind right now. But the one is called Fermat's Last Theorem. Basically, let me ask you this: what kind of a proof was it? Remember, we had like a direct proof, we had contrapositive proof, we had contradiction. Yeah, Colby. What kind of you're not sure? So okay, let me just kind of say the basic approach. Essentially, Andrew Wiles, so this is kind of the summary of what we learned. Andrew Wiles wanted to prove Fermat's Last Theorem from the time he was a boy. His advisor, John Coates, said, "You're an idiot. Don't work on that," right? No one can prove Fermat's last theorem. Work on something that you're actually going to make progress on. So he said, why don't you work on elliptic curves? That's kind of a hot field in number theory. Work on elliptic curves, yeah? Okay. So that's what he did. He did all of his research in elliptic curves. It's an area of number theory. And by the way, number theory is where Fermat's last theorem resides, okay? Well, Taniyama and Shimura were studying something called modular forms, which seemed like an unrelated branch of mathematics. It has to do with complex analysis, things like that. But then what they showed was that elliptic curves and modular forms are connected. And in fact, the conjecture was that all modular forms are kind of elliptic curves in disguise and kind of vice versa. There's sort of like a correspondence between the two, yeah? That was a conjecture though, right? Taniyama made that conjecture. He just, in this burst of insight, Taniyama actually ended up committing suicide at some point, right? And so Shimura was the only one kind of left from the Taniyama-Shimura conjecture. And so that was an open problem. It's conjecture that modular forms and elliptic curves basically are the same animals in disguise. Meanwhile, someone by the name of Frey, not this Frey, in Germany, said that if there was a solution to the Fermat equation, remember it's like x to the 3 plus y to the 3 equals z to the 3 or to the 4 to the 5, whatever. If there was an integer solution to that equation, then it would give rise to a really weird elliptic curve that wasn't modular, yes? So in other words, if there was a solution, it would give a counterexample to Taniyama-Shimura, yeah? If there was a solution, it would give a counterexample to Taniyama-Shimura. Therefore, and what did Wiles know immediately? If he could prove Taniyama-Shimura, then what? Then there would be no solutions. Now, what is that? Logically, what is that argument? It's the contrapositive. Do you see what I'm saying? So he said it's like, if there's a solution to Fermat's last theorem, then there exists an elliptic curve that's not modular. Yes? Then there exists an elliptic curve that's not modular. But if Taniyama-Shimura is correct, namely that all elliptic curves are modular, that would imply that there couldn't have been a solution to Fermat's last theorem. Yeah? To the Fermat equation. That's it. So yeah, it was the contrapositive of it. So immediately Wiles was like, man, I'm going after Taniyama-Shimura, right? There was one little breadcrumb that needed to be plugged, and that was done by Ken Rabe, that Berkeley mathematician. There was something called the epsilon conjecture, which basically, Frey was kind of a sloppy mathematician. He just kind of said, yeah, it's basically, it's an elliptic curve that's not modular. Yeah, you know what I mean? And but actually establishing that became known as the epsilon conjecture. Yeah, actually proving what Frey was purporting, namely that you have this weird example. That was an open problem for a while that Ken Rabe actually solved. Yeah. So once that piece was kind of wrapped up, then Wiles knew, I know what I have to do. I have to prove Taniyama-Shimura. Now there was all that stuff about like, using, Flock-Calveigen and things like that to try to actually do things. It didn't work. And then he went to Iwasawa theory and all this other stuff. I understand that that's kind of tricky, but the basics make sense, right? It's basically a contraposition argument, which is amazing, okay? And the argument comes from an area of mathematics. Doesn't really seem like it has anything to do at all to do with Fermat's last theorem. So I think that's fairly remarkable. So you have any thoughts? Any thoughts about it? Online as well. I mean, if there are people online that want to say something, that'd be great. Yeah, Monique.
I don't understand how Fermat's last theorem has anything to do with modular forms or the elliptic curves.
Yeah, so Monique says, what does Fermat's last theorem have anything to do with elliptic curves or modular forms? Well, you could at least see, I mean, let me just say this. And by the way, questions like that are precisely the sort of thing that Simon Singh's book addresses. He kind of gets into the weeds a little bit, and it's not difficult, amazingly. But when you look at Fermat's last theorem, you know, things like x cubed plus y cubed equals z cubed, that's an equation, right? Right, so I mean, and you could actually sketch that curve. You see what I'm saying? So, I mean, it's not surprising that that equation, if indeed there was equality there, that equation would give rise to a curve of some kind, right? Like you could plot all x, y, and z that happen to satisfy this thing. That's the best explanation I can give without really getting into the weeds. Simon Singh does a much better job than that, though. He goes a little bit deeper, but that's the thrust of what the connection is. Now, again, you know, I don't even really know necessarily what the bridge is between elliptic curves and modular forms. That's a little bit more mysterious because that involves two pretty disparate branches of mathematics. It's like you have this planet over here and this planet over here that seemingly have nothing to do with each other. And what Taniyama and Shimura said was, no, actually there's like a bridge between these two. Yeah. So other questions or comments? Yeah, Colby.
So they proved that like it's true, but do they know any solutions to like x to the n plus y to the n equals z to the n?
No. So the conjecture is that there are no solutions. So Fermat's last theorem is that there are no solutions for x to the n plus y to the n equals z to the n for n bigger than 2. Now, there are lots of solutions for n equal to 2. Those are called Pythagorean triples, right? But the conjecture is that there aren't any for n bigger than 2. And again, what Fry exhibited was that if there was one, it would give rise to a bizarre modular or a bizarre elliptic curve that was not modular. Yes, and so Wiles knew that he had to show that indeed all modular forms were elliptic and vice versa. And that's why he was talking about this correspondence. Yeah, and if you could do that, then he knows that no such solution could possibly exist. Yeah, so Fermat's last theorem is that there are no integer solutions. Integer solutions. It's easy to find like non-integer solutions, right? I mean, we could come up with one right now, like, pi to the 4 plus, e to the 4, okay, equals, this is some kind of number, correct? I don't know what it is. I'll call it c, yeah? And of course, I could just write that as the 4th root of c raised to the 4th, yes? So in other words, x equal to pi, y equal to e, and z equal to the 4th root of this horrendous thing, yeah, is a solution to x to the 4th plus y to the 4th equals z to the 4th. But that does not violate Fermat's last theorem because x, y, and z are not what? Integers, right? They are wildly outside of the realm of integers, yes? Okay, so Fermat's last theorem says that there aren't any integer solutions, yes?
Could there be rational solutions, but not integer? Or is that been disproven at all?
Rational solutions. So you mean like non-integer rational solutions? Man, I feel like the answer is no. In fact, no, because if you had a rational solution, you can multiply through the whole equation by the a denominator, clear it, and you raise it to the power of 4 so that you get a perfect 4th power, and then you would produce an integer solution to the, yeah. I'm using 4th power, but really Fermat's last theorem is any power. By the way, there was a lot of progress made on this before Wiles. It's not as if it just sat around for like hundreds of years and nobody did anything. Like Sophie Germain, you saw her mentioned, yes. By the way, One time when I teach this class, I'm going to focus a lot on her. She's amazing. I mean, she was really kind of suppressed because she was a woman in her day, but she was literally probably the smartest person on the planet, her and Gauss at the time. Gauss was just a jerk, okay? But she would write to Gauss quite a bit under a pen name, a male pen name. And like he just was super impressed with her. And she actually did Fermat's last theorem for a certain class of powers. I can't remember, like maybe powers that were congruent to 3 mod 4 or something like that. So she actually did prove Fermat's last theorem in certain cases. Eventually Gauss figured out that she was a woman, and then he was like, well, she's pretty awesome, so that's okay. and he kept corresponding with her. But Sophie Germain's a pretty impressive mathematician for sure. There were other mathematicians who made incremental progress on it, but no one had been able to prove it for all powers. That makes sense? Even Wiles, remember he talked about the 3-5 switch? At one point he was like he had to switch from the prime 3 to the prime 5. It's not clear exactly what he meant, but that's the sort of thing mathematicians do, is they'll try to really hone in on one case, kind of sort it out, and then maybe switch over to another one later on, and perhaps have to use a different approach there. Okay, so other questions and comments? Yeah.
It's kind of off topic, but what do mathematicians that don't like solve anything? I'm sure there's some like that. How do they make money if like, they're not making any work? What do they do with their life?
Well, okay, so if a mathematician doesn't solve some major problem, what do they do with their life?
Yeah.
Well, what am I doing with my life?
Oh,
So, yeah. I mean, I've solved stuff, but not like that, right?
They just like work at university.
Well, they could. I mean, there's also, I mean, there's a lot of, like, for instance, I was going to go work for the National Security Agency. When I first graduated, in fact, I had an offer to go work for the National Security Agency, but the issue was they couldn't really tell me what I was going to be doing, which was sort of troubling. Okay, but I mean, you can do research without it actually being like earth-shattering the way that Wiles was, for instance. So these guys aren't even necessarily trying to chase money around. Like, I don't think Wiles really cared that he was going to get like $1 million for solving this problem, you know? He doesn't care about that. He just wants to solve the problem. But there are, I mean, there's always, I mean, everybody that has like a PhD in mathematics has created new mathematics. That's the requirement for getting a PhD, is to create something new. In any discipline, is to kind of create something new. That might sound strange to you that new mathematics is always being done, but it is. In fact, like new areas seem to kind of raise up out of thin air, you know, because just out of necessity sometimes. You know, the computer revolution really changed mathematics. The focus of it, probability became really, really important. People started really kind of trying to pin down how to make things work efficiently, and that involved a lot of mathematics. Cybersecurity is a huge deal now, and so lots of effort has been made in the area of number theory, trying to find new ways to to hide information from evil people, right? And now, weirdly enough, I don't know if you know this, but actually some of the newest cryptographic inroads are being made in the area of quantum mechanics. Quantum mechanics. It's just bizarre that that's the case. So you have to go understand things like quantum physics, physics at the quantum level to sort of understand the frontiers of cybersecurity at this point. Dr. Hammond sometimes will bring in speakers that will talk about that issue. There's something called quantum computing that's a big deal right now that involves tons of mathematics and physics. There's a lot of speculation. Remember the problem I said about factoring numbers being like the crown jewel of prizes? You'd be the most famous person of all time for a while till you were dead, right? Turns out that quantum computing seems to be a way that that problem could be solved efficiently. Factoring numbers. No, just like what's an efficient way to factor numbers? Like if I give you a huge number, I say factor it into primes. What's an efficient way to do it? An efficient is not, I'm going to check all the numbers. Yeah, that's not efficient. Yes. Huh?
Something called Shor's algorithm.
What do you mean in quantum?
Yeah, I mean, there's a method of Shor's algorithm for regular computers, but it's nowhere near as efficient unless it's used.
Yeah, well, that algorithm is, I mean, there are some algorithms, by the way, that at first glance appear to be doing something efficiently, but really it's just a way of organizing the steps that you take. And Shor's algorithm is something that does that. There's another algorithm called branch and bound, and that involves, I don't know if you ever heard of the traveling salesman problem or something. It's trying to find like the shortest path to visit a whole bunch of cities. That's another open problem that if you solved it, you would be probably the most famous mathematician of all time. There are algorithms to help you do that, but they're not efficient. That is, they're not really better than just checking everything.
Right, but I think that algorithm, Shor's algorithm, if used on a quantum
Yeah, that's right. That's right. So that algorithm, if used in a quantum system, would do it. I think that's the speculation. Yes. Yeah. But that's above my pay grade. I need to learn about that kind of stuff. But quantum stuff is really interesting. The basic principle is, like at the quantum level, you can always tell if something has affected the system from the outside. Okay, it's kind of like you have these particles going across or something, and someone would have to come in and listen, and even in listening, they would disturb the system, and it would cause the particles to kind of change course and things to change in the system. You can tell that that's happened. Okay, you guys have probably heard of something called the Heisenberg uncertainty principle, for instance, and that's talking about things happening at the quantum level. So you could go take quantum now. I think they might call that class thermodynamics here or something like that, but that's interesting stuff. So that's on the frontier as well. So like I said, new mathematics is being developed all the time, which is kind of interesting. In fact, Dr. Fry and I we just wrote a paper on divisibility tests that he may or may not have you read in one of his classes. It's funny because sometimes you'll just think of something offhand because of something. In this case, it was actually a mistake that was in my notes, and I started thinking about it, and I was like, man, I wonder when that is true. And I started kind of thinking about that, and Dr. Fry and I started talking about it, and we wrote a paper about it. So that sort of thing happens in mathematics a lot. Okay, new frontiers. Other questions?
So you mentioned that like there was a common mistake that a lot of people had like when trying to prove it, and like you think that Fermat even made that mistake. Can you like explain that generally or why?
Well, okay, so there's a common mistake, and it involves kind of like an incorrect use of some like algebraic formulas is the essence of the argument. And there's tons of them. Like if you go, there's something called archive, arxiv.org. Okay. And people post papers there while they're in review, because sometimes a paper will be in review for years. Dr. Fry had a paper in review for like 8 years. was like a 50-page paper, and it just took the referee 8 years to actually carefully work through the whole thing. And then it was like, oh, he almost like forgot that it even existed. And then suddenly it was like, oh, hey, we're finally done reviewing this paper. But if you go here and you look up like Fermat's last theorem or something like that, sometimes you'll stumble across people that think they've found a short proof. That's probably the one. That's the one that a lot of people think Pierre de Fermat actually did. But it's kind of hard to believe that he would have been that silly, because he was really impressive. But I don't know. Yeah.
How do you get qualified to be selling your reviews?
When you to review papers, that happens when you actually start writing papers, and people start to know you, and then they're like, oh, hey, there's like an editor that will say, oh, hey, would you mind reviewing this particular paper? Yeah. A lot of times it's called double blind, like where I don't know who's reviewing my paper and they don't know who I am either. Does that make sense? Sometimes it's single blind, where I don't know the reviewer, but they know who I am. That happens sometimes too. Mathematics has its own, it's like its own little culture in that way, for sure. Right, other questions? Yeah.
It's not really a question, but I really like the whole point at the end that even though they did solve Fermat's last theorem and figure it out, like they know that couldn't have been how he did it, because all the math they used
Was new?
Yeah.
Yeah. Yeah, right. So, I mean, it does seem like that the way that Wiles solved it, I mean, there's no chance that that Fermat did it that way, right? So the speculation is he made this mistake. That's pretty common. I don't know. Maybe there is a simple argument. I mean, he was a master. Kind of, he wasn't quite on the level of like an Euler, for instance, but he truly was a master. And it's hard to believe that he would have made such a crude, ridiculous error. But I don't know, maybe he did. Maybe he did, but maybe there's a real simple argument out there that someone just hasn't seen. Yeah. We may never know. Sometimes, momentum gets lost once something is solved. So people stop looking. But Wiles did it. If you want to read about another interesting guy, you can look up Grigory Perelman. I think that's how he spells it, Perelman. Okay. He's a Russian mathematician, and he solved something called the Poincaré conjecture about 10 years ago, maybe 15 years ago or something. That was a long-standing one, and everybody was shocked when he announced he had solved that. I actually have, I'm not going to do it today, we don't have time, but I actually have a movie of Flatland. So next week, I do want to spend some time kind of wrapping up the Flatland discussion. But one thing I'll be interested to get your take on is whether the movie is actually accurate. It's short. It's only like a half hour long. So yeah, that'll be some fun discussion. Okay. They try to do some stuff with like, explaining the culture of Flatland, things like that, very briefly, like at the beginning. But the main focus is on the second half of the book that you're reading. So yeah, we'll watch that next week as well. Other comments? Yeah, Charles.
The question about the class, when you said there's one test left, is that like a test and the final, or just like one test overall left?
Yeah, so it's both a test and a final test. Yes.
Okay, it's all in one.
Yes.
Okay.
It's one test and it's the final test. Yes. Yeah.
The weight all shifted it out one test for the reconstruction.
Well, I don't know. I mean, I'll do some, you know, look, I mean, I'm a just and merciful instructor. So, you know, I wouldn't worry too much about that. I'm not going to actually hurt you. Okay. I'll look, and I won't just do it like willy nilly. I'll look and make sure. I'll be like, okay, is this going to hurt, you know, is this going to hurt them or not? And then if I determine the answer is yes, I won't go, ha, 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 hurt you, right? I won't do that, okay? So yeah, Colby. What did I do? Well, I work in an area called combinatorial chance, okay? There's a class here called combinatorics that I tend to teach. It's more like discrete math. Discrete math is essentially mathematics concentrated on listable objects, like countable objects. Most of the time, the sets you look at are finite, actually. And basically, you look at collections of objects that are all similarly built. So in particular, I look at things called permutations a lot. Permutations is basically if I have some number of objects, you know, 5 that are all different, I say, how many ways are there to arrange those things? The answer is 5 factorial, 5 times 4 times 3 times 2 times 1. You put 1 first, and then you have 4 options for the second, 3 for the third, 2 for the fourth, etc. And so I look at permutations of a certain size or length, and I ask questions about them, like, you know, what sorts of properties do they have? And in particular, what I did for my PhD was I did something with sorting permutations. So like if I have something, you know, if 5 is first and then 1, 3, 4, 2. So 5, 1, 4, 3, 2. That's like out of order, right? 1, 2, 3, 4, 5 would be in order. So 5, 1, 4, 3, 2, you can kind of put that in order, or in order by like exchanging elements. Do you see what I'm saying? Exchanging numbers. And I looked at that operation of exchanging numbers around, and I asked simply the question, as I'm sorting one of these permutations, as I'm kind of sorting them by exchanging elements, what's the likelihood that I'm going to stumble upon some other permutation that I'm concentrating on? Okay. So like so give me 2 permutations randomly, and I start to sort the one. What are the chances that I'm going to stumble upon the other one in the process of sorting the one? Does that make sense? That's the essence of what I did, and I showed that it's not very likely at all. It's like almost 0. Okay. I looked at, that's the essence of what I did. So if you go and you look for my dissertation, it's called On Comparability of Random Permutations. Okay. And that's the essence of what's happening. Comparability of them means as I'm sorting the one, I stumble upon the other one. I would say that those 2 permutations are comparable, okay, comparable. So that's what I did. And I've done several things that kind of extended that as well. Hopefully that makes sense. I had to explain that one time to a bunch of non-mathematicians. And that's kind of the basic explanation I came up with. Because you can really talk about it in a way that's impenetrable, but hopefully that made sense. Other questions? Well, I was going to do one other thing. I'm not going to do it, though. I was going to show you why, just because Journey Through Genius didn't do this, I was going to show you why sine of x is equal to that infinite polynomial expression. I'll probably show that to you, though, before the end of the class for sure, just because I think that's a good thing for you to see. And plus, it'll force all the Calc 2 people to review some power series stuff, yeah, which they'd better be doing. But who's presenting on Friday? Yeah. Okay. So Charles. Okay. So is it just you?
Me.
Oh, sweet. Okay. So you 3. Okay. And so you're talking about Euler again, right?
Yeah.
Awesome. Okay? And basically Euler's crazy number theoretic joscillations, right? I mean, he was just so powerful computationally. It's almost unbelievable. Okay, so it's an interesting chapter, and that will frankly be the last one. And I think they're the last one in Journey Through Genius. I sent an article on the Cantor set. So for the group that remains, I think there's one group that is sort of remaining. That will be your topic, and that's man, that is a gift, believe me. The Cantor set's awesome. You should have plenty of fodder there for a little presentation. Yeah, it's one of Georg Cantor's great gifts to the mathematical community was the so-called Cantor set. Okay, so we'll have a look at that. Okay, cool. I'll leave it at that.